Yeah, class. Okay, so we're going to talk about electric currents today. So let's say we have a metal conductor, like say a copper wire. And we apply a potential difference between the two ends of the wire. And let's say that this is at the lower end, so we'll call this 0. The other end, we'll say that's at a potential V. So potential difference of V between the two ends of the wire. And we know that there's going to be an electric field, going from high potential to low potential. So, we've talked about conductors before, where they have a lot of free electrons that can easily move around. And so what's going to happen is, the electrons that are free to move are going to do so. And if you look at like a particular electron, remember the force on an electron is in the opposite direction of the electric field. So just to label this, that's the electric field. And so what we'll end up with is a bunch of electrons moving to the left. Now, I should point out this is not actually an accurate picture of what's happening inside this conductor. You can visualize you have all these atoms and all these electrons and everything's just sitting there. And then when you turn on the electric field, these electrons just start going to the left. But that's not really what happens. The electrons are moving around before that electric field existed. Like let's just say, as a simple example, say we have an electron moving to the left and another electron moving to the right. There's going to be no real net flow of charge. You have, let's say we, instead of just 2 electrons, say that we have a large number of electrons. Some are moving to the left, some are moving to the right. Now, they don't have to move along the wire, though, because the wire has a finite thickness. So really, they can be moving in any direction. But on average, let's say we have one going in this direction. They're going in all directions with no preference. And so if you have a large number, for everyone going this way, you'll have one going that way as well. And, or in the exact opposite direction. So overall, the electrons are just moving around in a completely random fashion. And so there's no net flow of charge from like one end to the other. And so now when we create this electric field, we say these electrons are going to move to the left. Not necessarily. Some of them are still going to be going to the right. But the effect is, like say we have this electron that was going to the right. Now it's going to slow down at least because of this electric field. Or this one was going, to the right at some angle. Well, its path will be deflected a little bit. So it's not going as far to the right as it did before. Meanwhile, these are going to be, deflected in this direction. This one's just going to accelerate in the, towards the left. So what this external field is going to do is it's going to shift all the electrons to the left, their motion. So you can think of it, the electrons as like a gas, almost. If they're free to move around, they move around totally randomly. If there's no potential difference between the ends, they move around fairly randomly, and so there's no net flow of charge. And then when you apply an electric field, it kind of shifts things to the left. And so there's going to be a net flow of charge, or a net flow of negative charge towards the left end of this wire. And we call this flow of charge a current. So to define current, we use the letter I for current. I guess C is commonly used for just any constant. So for whatever reason, they picked I for current. And that's defined to be, I'll just write it down, say delta Q over delta T. So what does this mean? Let's say we have an imaginary surface here. and we look at the net flow of charge across this surface in some time interval delta t, like say 1 coulomb in 1 second flows to the left. And that would be a net flow. So we'd have to take like the total amount of negative charge that are crossing to the left, but also take into account the ones crossing to the right, which would partially cancel that out. But the net flow of charge would be delta Q in whatever time interval delta T that we pick. And the units for this, I'll write that below. We measure current in amperes. We use the letter A. So Ampere was a scientist in the 1800s. They named this unit after him. So it's called an ampere, or an amp for short. So that's our current measured in amps. And charge is coulombs over time. So the basic SI unit we have an amp is a coulomb times a second. Okay. However, we're not quite done with defining electrical currents because there is a bit of a problem here. And then we're talking about the flow of charge across some surface, but current has a direction as well. And there's also two types of charges. Like here we have a net flow of charge to the left, but they're negative charges. What if we had positive charges moving to the left? That would be a very different case. So again, let's look at this simplified picture. Let's just say that we have a bunch of electrons that are flowing in a nice, steady, they're all just moving to the left. What if we had a similar situation, except these were positive charges moving to the left? The results would be very, very different. In this case, we'd have negative charges flowing here. The other case, like say we put a plate on the end, we'd be charging this plate with negative charge. If we replace this current with positive charges, we'd give a positive charge to this plate. And so the results are very different, so we need to take into account the type of charge as well. And so it kind of makes sense that we define current to be the direction that a positive charge would be flowing. So if we have a bunch of positive charges flowing to the right, this would be a current to the right. Here we have negative charges flowing to the left. This is a current to the right. So if you have positive charges moving, the current is in the direction of those charges. If you have negative charges moving, then it's the exact opposite. And it's kind of unfortunate that it turned out the way it did, because we have two types of charges. So you might think there's no real reason to give preference from one type over the other, except there actually is. Because most of the time, it's electrons that are moving. Electrons are small and light, and they can move very easily. Positive charges do not flow nearly as readily as electrons. So, like if you look at this copper, for example, or aluminum, some conducting metal, it's like the positive charges are all fixed in location relative to each other. They form this lattice, or like a particular structure, where most of the electrons are kind of stuck to that structure as well, except some of them are free to move around. So you don't really see currents of positive charges flowing. Now you can ask the question, what if I just take this whole conductor and move it to the right? Well, then you got positive charges moving, but the negative charges are moving with it, so there's no net effect there. Now, you do occasionally come across currents made by positive charges moving. Like in a chemical reaction, you can have positive ions going in a particular way, like with a preference to go in a particular direction. And so that you can occasionally come across a current where there's positive charges moving to the right, like in the direction of the current. But in the overwhelming number of cases, it's negative charges that move in the opposite direction. So why did we define things this way? Well, historically, it goes back to Benjamin Franklin, And he never heard of protons or electrons. They were not known at the time. They didn't even know about atoms back then. So he had no reason to, he picked positive charges, probably just based on friction. I'm not sure the history there. When you rub things together, you know charge can transfer from one to the other. And you can pick one arbitrarily and say, well, this rubber object acquired a positive charge, the other one acquired a negative charge. Like say glass and wool or something. There's no way to know what these charge objects were in the period. So he arbitrarily said one of those had a positive charge, and now looking back, it would have been much better if he did things the other way around. So it would have been better if maybe we defined protons to have negative charges and electrons to have positive charges. That would have been better. But we're stuck with this for historical reasons. So we also talk about something called like a conventional current, because what's actually going inside of this conductor is fairly complicated. And you can kind of picture it as like an electron cloud, or there's like gas of electrons moving around. And they just have a slight preference for going this way, but it's not this orderly picture where these electrons just go from one end to the other. A lot of them are still moving to the right, and so when I think of currents, even though I know it's electrons that have a preference to move to the left, not that they necessarily are moving to the left, but I like to just think of a current as a nice flow of positive charge in the direction that the current is going. So I know that's not a realistic picture, but it gives you the right results, and it's just kind of easier to think of it that way. Okay, so we define current, delta Q over delta T, like the rate that charge is flowing, like the number of coulombs that will pass some marker and a certain time interval. Now, in, say, this conductor, what factors could affect the, let's kind of redraw this picture, where we have this potential difference between the two ends, so there's an electric field, which is driving the current. What factors will affect how much current we're going to get? And I'm just going to write down a couple, like, right now, I'm going to just state that the potential difference, or here, let's say the current is proportional to the potential difference. So if you establish a certain potential difference, say you get a current of 1 amp. If you double that potential difference, you get a current of 2 amps. This is something called Ohm's law. And it turns out that Ohm's law is not actually true. It's more like a good approximation for a great number of materials. So I'm going to kind of revise that statement later. But this is basically a statement of Ohm's law, that if you double the potential difference between the two ends of a conductor, you double the current. But we're going to revise that later. Okay, so that's one assumption. We also have to look at the details of the conductor as well. Like say we have the conductor has a length A, or length L, and a cross-section area A. How do these factor into the current? And the current is also proportional to this cross-section area. So if you have like this cross-section area, like a current flowing this way, if you just have or say this is like a wire, if you have a thicker wire, you get more current flow. But it's inversely proportional to the length. And so we can combine all of these things and say that the current is proportional to VA over L. Now, I actually want to rewrite this a little bit, though. Let's solve for V. So, putting it another way, we can say that the potential difference is proportional to IL over A. Now, there's one other factor that that has a huge effect on like what the current would be, and that's the material itself. Like if you apply potential difference between, say, a copper rod and then, say, like a plastic rod, you will get enormously different results because one's a conductor, the other is an insulator. And so to take into account the material, we have this new constant called the resistivity. So again, to turn a proportional relation into an equation, we add a constant. And so we can say overall, actually I don't want to write that down yet, I'll just put it here. So now we're making this an equals sign. So this is a Greek letter rho. This is called the resistivity. And I'm just going to write down a few values for resistivity. A couple different materials. And again, whenever you have data like this, you have to look at how this data was collected. So again, these values I got resistivity of various materials. This is at a temperature of 20 degrees Celsius. Turns out that temperature can have an effect on the resistivity of a material as well. So this is just taken at a particular temperature. We usually don't worry too much about those kind of details. So we're just going to say, we just have a table, we look up these values. So let me clean this up a little bit. Let's just write our basic equation. Okay, so just some values. So the units for resistivity are ohm. This is called an ohm. So this is a measure of how much resistance there is to the flow of electricity. And this was named after a guy named Ohm. It's called Ohm's law. So that's a new unit we have. So this rho L over A. Let's look at that for a moment. We'd have ohms times meters. The length would be in meters, and the cross-section area would be in meters squared. And so we get the voltage, potential difference between the ends, is something measured in ohms times the current. And that is called Ohm's law. So we call this, this rho L over A, we call that the resistance and use the capital letter R for resistance, which is measured in ohms. So from this we have a volt is equal to an amp times an ohm. Okay, and that's called Ohm's law, and this is what we use more often than this one. So again, this kind of takes everything into account. If we have, say, a copper wire, the dimensions of that copper wire will also have an effect. But we don't want to have to do these kind of calculations all the time. So usually, how we actually use this equation. You can buy resistors. Like they sell these things commercially. You can buy like a resistor of like one ohm or 100 ohms or a kilo ohm or 670 ohms. They sell these in a huge variety of numerical values. And so a lot of times your resistor is just, your resistance is just something that's known. Another thing, it's something that we can measure, especially nowadays. There's these devices where you can just measure the resistance across something. So if you just say have like a conductor and you want to know the resistance, instead of calculating it, very often you would just measure it, or you have some commercial value. So usually we don't use this version. We just to find the resistance of an object, which takes into account the type of object and the dimensions of it. So this is the more commonly used version, and that's called Ohm's law. Okay, so let's get to this table. So we've got material and the resistance, or sorry, the resistivity in ohms times meters. So the most common conductors that we use are copper and aluminum. So let me start with those. Copper is 1.72 times 10 to the minus 8th, and aluminum is 2.82. So aluminum is actually a little bit better of a conductor than copper. You might be more familiar with copper being used as like copper wire, but yeah, I think it's just used because it's cheaper. I'm pretty sure those like power lines, like the the ones you see when you're driving down the road, I'm pretty sure those are primarily made out of aluminum. And gold is also a good conductor, and that is used in some devices as well. Obviously, that's more expensive. Let's see. Yeah, we've got metals. I look at there's kind of an extreme. We've got nichrome. This is an alloy. Looks like it's a combination of nickel and chromium. So these are like on the periodic table. These are elements. This is an alloy. It's a combination, which I'm assuming is nickel and chromium. That is 100 times 10 to the minus 8th. So this is an extremely good conductor. And I'm guessing it's fairly expensive. It's not used nearly as often. Okay, so these are all metals, and these are very tiny numbers, which means that the resistance is going to typically be small. So there's not going to be much resistance to this flow of current, which is usually something that we want, or often something we want. So if we want a current, we want to use something that's a good conductor. I'm going to write another one, something called germanium. Actually, I use silicone. Silicone, now this one has a range anywhere from 200 to 2300. And let's just kind of ignore that for a moment and move on, but I definitely want to come back and talk about silicone. And then let's look at like wood. I'll write down two wood and rubber. So wood, it says maple, 3 times 10 to the 10th power. And rubber, this is 10 to the 13th to 10 to the 16th. So that depends on what type of rubber we're talking about. And so here we've got things like 10 to the minus 8th power. These are called conductors. Very low electrical resistance. Down here, look at wood. 10 to the 10th power compared to 10 to the minus 8th. That's like a billion times as high as something like wood is about a billion times the resistivity of aluminum. So that's an enormous difference. Now something like silicone, that's actually in the middle. So these are called conductors. These are insulators. Silicone, something in the middle. This is called a semiconductor. And why does this kind of category in the middle exist? And it's actually fairly complicated, but if you look at silicon, or if you look at, say, copper, remember, like every atom gives up one electron that's free to roam around with very little resistance. And because there's so many atoms here, you have a virtually unlimited number of electrons that can just move around, and so a small potential difference can have a very significant result here. If you look at something like silicon, there are a number of electrons, but it's much smaller than one per atom. Typically, it's caused by impurities. Like if you have silicon, there's some other elements that get mixed into that. And so you have a small number of impurities that can give up these electrons. So like here you have one electron per atom. For a semiconductor, maybe it's like one electron per billion atoms that is kind of free to move around. Again, a bit of a simplification here because temperature is also a very significant effect when it comes to semiconductors. And there's even different types of semiconductors. Like some give off, positive charges are free to move around, some give off negative charges. But yeah, this is actually an extremely important topic because of electronics. Heard of Silicon Valley. These are used in modern electronics like computers and microchips and all that. So very important, but a fairly complicated topic by itself. Okay. Now I mentioned something before. Here we have Ohm's law, where you say like the voltage and the current it produces are proportional to each other. And then I said that's not exactly true. And it kind of comes down to how you define things, because Ohm's law is extremely useful. And so what we do is I'll reverse that later. If you were to plot, say, the current or no, let's say we plot the current as a function of the voltage. Well, we'd have a line going through the origin, or we'd have a point at the origin. If the voltage is 0, the current's going to be 0. Then if we increase the voltage, we'll get a current. And if we plot it and it looks something like this, this is called an ohmic material, where it's just a linear relation. However, there are devices, or some materials where it's not linear. So maybe we'd have a second material where it looks something like this. Or I think maybe more realistically it would look so here, this would be called an ohmic material, and this would be a non-ohmic material. And so in this case, if we say that this object has a resistance of, let's just say 100 ohms, then Ohm's law is simply not valid, because we can see that the voltage and the current are not directly proportional to each other. However, we really like Ohm's law. So because a great number of materials, we have this linear relation. And what we do is we actually define resistance. So by definition, we say that the resistance of a material is the voltage over the current. And so, in that sense, Ohm's law automatically is valid. Because by definition, the resistance is voltage over current, and you can just rewrite that as V equals IR, and so now it's automatically true. And so, it just turns out to be more useful to define resistance this way. And so in this case, for an ohmic material, the resistance would be a constant. Where for a non-ohmic material, the resistance would depend on the voltage. Like on this, if we define the resistance as the voltage over the current, then on this graph, the slope would give us 1 over R. And so here, if we have a line, we have a constant slope, that means that a constant resistance. So again, here the resistance would be 1 over the slope on this graph. Let me just double check, make sure it's 1 over the slope. Yeah, if you plot the voltage as a function of current, then the resistance would be the slope. This one's kind of upside down. So yeah, the resistance is 1 over the slope. But again, if the slope is constant, resistance is constant. So for this material, we can see that the slope here is different than the slope, say, at this point. Like here we have the slope is smaller, which makes the resistance higher. And so, again, the resistance changes as we change the voltage. We call that a non-ohmic material. An example of a non-ohmic material, or a non-ohmic device, would be like a normal incandescent light bulb. If you turn it on, and I'm pretty sure the reason why a normal light bulb does not have a constant resistance, they heat up very much. Like those old incandescent light bulbs, you have a filament that you heat up to, I believe, a few thousand degrees. And so that, when the light's off, it's at room temperature, and then when you heat it up, it goes through such a great temperature change that that'll affect the resistance. So I'm kind of just assuming that that's why a normal light bulb does not obey Ohm's law, but that's kind of just seems reasonable to me, but yeah, I never actually looked that up. But I have to clean the board after this. Okay, so yeah, so what we're going to do in the class is just define resistance to be voltage over current, and then Ohm's law is always valid. So yeah. Let's talk about one more thing, and that'll be it for this lecture. And kind of ask, what is, one of the main, what do we use electricity for so much? And, you plug something in the outlet, what are you trying to get out of that outlet? And basically, electrical currents carry energy. So we want to talk about the power of, the power delivered by a current. So a power is defined as how much energy you are delivering. It's energy over time. So let's say U is the amount of, or the delta U is the amount of energy that you're delivering to, say, some device in a time delta T. And remember, delta U is equal to Q delta V. So you think about, a current's actually charges moving through a potential difference. So the energy that would be delivered would be the amount of charge. Let's call that delta Q. Or actually, I'm going to redraw that picture. So we have a conductor here with a potential V between the ends. So we just called that V, even though it's a potential difference between the two ends. Since one of the ends we just arbitrarily set to 0, we say there's a potential V across these ends, we just call it V. And so say in a time delta Q, the total amount of charge that flows through this wire is delta Q, and then, because it's power, we divide by delta T, and we can break this up into pieces. We can say this is delta Q over delta T times V. Now remember, delta Q over delta T, that is our definition of current. So what we have here is the power delivered by a current is the current times the voltage. So P equals IV. So again, this is important because this is kind of the whole point of electricity, is it carries energy from one place to another. So a very important result here. Power is current times voltage. Now, one more thing I'll mention, we can write this in different ways by combining it with Ohm's law. So this is kind of our basic equation for power. Power is current times voltage. Now we could do this. We could say voltage. Here, power is current times voltage, but the voltage is I, so we could say I squared R. Or we could say I is V over R. So that's our current, and then times the voltage, where we would square that. So we have V times V, so we just write it as V squared. So these two are not on the equation sheet. Basically you have this one, and it's very easy to combine it and get the other two. So I'll just mention it here. But yeah, you could just put them together yourself. And yeah, I guess that'll be it for this topic. We just kind of defined things like current and resistance and resistivity. And then we're going to go on and talk about things like electrical circuits. Like we can look at some kind of simple systems where we could, actually deliver currents to objects. And overall, we're going to look at a very, very limited, just the electronics is a huge subject by itself. Some people just study electronics, like electrical engineers. We're just going to barely touch on that. So we defined current, then we're going to talk about some very simple electrical circuits. And we're not going to get too deep into the subject in this class. But yeah, that'll be all for this lecture.